and thanks for inviting me to actually attend this interesting symposium and present. Again, my name is Amir Haghverdi. I'm associate professor in the Environmental Sciences Department at University of California Riverside. And by training, I'm a biosystems engineer / irrigation engineer. So today I'm going to mainly talk about irrigation management and water conservation, and how to use technology or emerging technologies to actually enhance irrigation water use efficiency. I was afraid that after the rainfall that we got, nobody may show up for my talk, but it seems that we have more than 100 participants, so which is a good sign. So let me see if I can advance my slides here and use my laser pointer. Typically, when I present and give talks at international meetings or talk to colleagues from other states, I spend a few minutes to talk about the importance of water conservation, but I don't think there is a need to do that here. I'm assuming that most of the people attending are aware of the situation in California, that this water conservation is an important goal, and with the population that is close to 40 million, limited water resources that we have, and changes that are happening in the climate. And especially in Southern California, the available water resources are very limited, so we need to actually have water conservation as a priority, and the previous speakers actually set the stage for my talk. So when I joined UC Riverside 5-6 years ago, so I started doing some field work, and my background is mainly agricultural irrigation, but here at UC Riverside, we started doing some landscape irrigation as well. So here on the left-hand side, you can see the research sites that we built over the years, mainly in inland California, Riverside Agricultural Research Station, Experiment Station, and then also we had some research plots in Kearney Research and Extension Center, and then also in Orange County, we started a project in Irvine a few years back. And here are my students mainly that I wanted to acknowledge their hard work, and without their dedication and hard work, we would have not been able to actually carry out this project. So we started with some turfgrass irrigation projects, and then we switched to other alternative ground cover species. Right now we have more than 300 fully automated research plots, and looking at 16 to 18 different ground cover species. One thing that I wanted to just bring up, and then you probably noticed from the previous presentation that the rainfall that we get in Southern California is very limited and much lower than the evaporative demand, by which is 5 to 6 times higher than the rainfall. This is just a semester station, the network of weather stations that we have in California. This is for Riverside. I just pulled the data for this presentation. And you can see that the rainfall, the precip that we got yesterday was less than 0.2 of an inch, while the evapotranspiration, reflex evapotranspiration was 4 or 5 times higher for the previous week. So even now that we are happy, and I'm happy as well that we received some rainfall, we should know that the rainfall that we receive is not enough to fulfill the crop water requirement for the irrigated landscape, and we need supplemental irrigation. So most of these slides are for residential areas, but the concepts that I'll be covering are also related to irrigation in general, the concept of having healthy soil for an optimum irrigation management. So in a typical settings here in residential areas, we have irrigation supply lines that are providing water, and then we have some sort of a timer that typically you can program to close solenoid or electric valves on and off, that they actually let you to schedule irrigation, whether you have a micro irrigation or pop-up sprinkler heads most of the times. The problem is that typically they are not really in residential areas. We don't do a good job to schedule irrigation based on science-based information, and then waste of water could be substantial when we have rainfall and we still keep irrigating, or when we have over irrigating and we don't take the crop water requirement into account. So from the technological perspective, the smart irrigation controllers have been around for a number of years, and that's part of the research that we do. We try to understand how reliable these products are, and then how we can actually use them and tweak their settings to achieve the water conservation goals here in Southern California. So if you're familiar with the irrigation timer, if you add a sensor to it, that would be a smart controller. And typically, we can divide the smart controllers to two big categories. The first one is weather-based or evapotranspiration-based smart controllers that they basically use a temperature sensor or to calculate evapotranspiration or get evapotranspiration data from network of weather stations that are available publicly or privately. And then also soil moisture-based smart controllers that they use soil moisture data to regulate irrigation. So for the weather-based controllers, they actually use this concept of ET, that is a combination of evaporation from the soil surface and transpiration from the crop, that we usually don't divide them. We just use the combined term ET because it's difficult to measure or estimate them separately, and then we use evapotranspiration as a standard term. You can get evapotranspiration data for a reference crop, which is typically a turf grass, cool season turf grass, from weather stations such as CIMIS, or some of these smart controllers, they come with a weather sensor that is typically has a temperature sensor that you can estimate reference ET. What is missing, or what we have been working on or identify as a knowledge gap, is that we don't have information about different species that we see in residential areas or in urban settings in general, in terms of how much water they use and how much of drought or deficit of irrigation they can withstand without basically using their functionality or seeing a drought injury and that would impact their aesthetic beauty. So that's a part of the work that we do, is to try to generate science-based information in terms of water requirement of different species. And I'm going to talk about this in a minute. So when you have an estimation of how much different species need, how much water they need, which is a fraction of this reference ET, you can program their controllers, and then they apply the right amount of water. And soil moisture-based smart controllers, as you can say from their name, you need to have a soil moisture sensor that basically eliminates unnecessary irrigation application. So whenever the smart controller tries to apply water, it checks the level of soil moisture, and if it's over the threshold that you need to program, then it just doesn't let the controller to send a signal and open this solenoid valve. So you would then, with that system, you actually can adjust or eliminate unnecessary irrigation, as I mentioned. So in the soil in the root zone, you can imagine, and we have great presentations about this, two extreme situations when soil that is super dry or wet and you have waterlogging. Basically, you don't want to see that from the irrigation management perspective and crop health. So what you want to see is a system that has soil particles and air and also water. So another way to think about it is to, or the way that we think about it, irrigation engineers for irrigation management, is to actually look at the saturation and dryness and try to identify some levels or thresholds that we use for irrigation schedule. So if you have a pot like this, you add water, you see that there is a gravity portion of the water that you apply. If you bring it up to saturation, that actually you lose that drainage or gravity water that goes to deeper layer here. It just, you lose it. So then you get to first stop that is really important. That's called field capacity. So that's the point that we usually, when we want to irrigate, we don't want to go beyond field capacity, because that would be the water that we lose. And then from the field capacity, that is start point, you have crop using water, uptaking water, you get to a point that we call it wilting point, permanent wilting point, that we don't want to basically go there. It's dry enough that plant cannot uptake water. So we want to stay between field capacity and permanent wilting point, which is available water. And typically we have a percentage based on the crop that you say, okay, I want to use, I don't know, 50%, 30%, 40% based on the different plant species and their characteristics of this available water. Another concept that I wanted to briefly talk about is about the irrigation zoning. So with this smart controllers or even with the timers, we usually in residential areas, even urban parks and even golf courses, you have a diverse system that with different species, ground covers, turf grass, trees that they need different irrigation management. So that is something that should be, we should take it into account when we actually design our urban green spaces and also irrigation systems. So we make sure that they are grouped based on their water need, which is typically not the case. We don't have them grouped, but based on the water needs, and the layout of the irrigation system is not actually optimized. But in an optimal situation, ideal situation, we can have different solenoid valves and parts of irrigation system that we can supply water to different hydro zones, if you will, that they need the same amount of water. And then with the evapotranspiration-based controller, then you need to insert that fraction of reference evapotranspiration for each hydro zone. And with the soil moisture sensors, ideally we want one soil moisture sensor per zone. So that was just a very short and brief overview of smart controllers. If you are interested in these products, there is rebate actually for residential areas. Most, at least in Orange County where I live, there's rebate. I'm sure there is in LA as well. So you get to get these products that are, I think, good tools to save water. And if you are interested in the science behind them, we actually put together an outreach publication that you can download from our website, ucrwater.com. This is a series of outreach publications on urban water management. This one is on smart weather-based controllers. We're working on another publications for soil moisture-based controllers. And the first actually publications was on understanding your residential water bill, if you want to know more about that. We had great presentations on soil compaction, and I just briefly talk about because this symposium was about soil and covering water, but soil, water, and plants, we look at it as a system. So we don't want to really have a compacted soil from the irrigation perspective, because that restrict the root growth. So then that impacts the irrigation management, and then reduce plant water uptake, and reduce the water holding capacity. And all those parameters actually decreases the irrigation water use efficiency. And then also low infiltration rate that we had a great presentation about that would increase the stormwater runoff and erosion, of course. And then also you won't be able to really minimize the runoff when you have a super compacted soil, even with cycle and soaking or other techniques that we use for irrigation management. So soil compaction and soil salinity, those are two important topics that came to my mind when I was thinking about the importance of soil and soil health and irrigation management. When we switch to alternative water resources, or when we have such as recycled water, which is necessary to use them for irrigation purposes, they usually have higher level of salt. And then what happens when we don't leach the salt to deeper layer, or when we don't have a drainage system and we want to conserve water, so then we may have some salinity issues. So basically, we don't want to have salt buildup in the root zone. It can cause toxicity, osmotic effect, which is basically makes it hard for plants to uptake water, and then you may see some nutrient deficiencies, and also impact on soil structure and reduce permeability, which increases the runoff. If you are interested in the topic of soil salinity, okay, I see that my 15 minutes up, but I'm going to go a little bit over time, so hopefully it's okay. To cover some of the research that you have been doing. So these are, again, two outreach publications on salinity and soil leaching that we did, and we can access them from my website for free. Also, over the years, as I mentioned earlier, we have been working on multiple projects. I'm not going to share the results here. I'm just going to at least not for all the projects, but I'm going to tell you what we have been doing. We started with this 2 adjacent turf irrigation projects, looking at evapotranspiration, smart controllers, ways to conserve water. And now my student, one of my students is actually looking at the greenhouse gas emission, CO2, and then trying to understand the trade-offs between water conservation, greenhouse gas emission, and also the efficacy of soil evapotranspiration based smart controllers. So we are pushing for implementation of new technologies such as this autonomous irrigation systems that they actually talk to smart controllers autonomously and flow meters to avoid or identify leakage, avoid loss of water, and avoid unnecessary irrigation when using the rainfall shut-off irrigation shut-off devices. This is another project that we started. This one, the first one was in Riverside. This one is Orange County, Irvine. We use recycled water. We try to see if we can autonomously conserve water using smart irrigation controllers based on soil moisture. This time with my colleague Darren Haver at South Coast Research and Extension Center. So, and then we also are looking at the impact of that salinity buildup when we practice deficit irrigation and you want to conserve water for these warm season turf grasses, and on infiltration rate. So one of my students is actually measuring infiltration and salinity buildup in this site for a number of years, and then these are all ongoing projects, so we are really interested in seeing the results and analyzing them. This is our most ambitious project, covering 12 ground cover species, alternative species from native species, and then our new introductions and the most widely used species with my colleague Don Merhat in Riverside campus. More than 300 soil moisture sensors at different depths, looking at crop physiology. This is my student installing TDR sensors. We are flying our drone, getting images to foresee drought injury, and then looking at the physiology of the plant species at plot level. Is a little bit of results before I wrap up. So these are some of the species that we have: honeysuckle, jasmine, lantana, buckwheat. You can see the origin, they're coming from different places. Primrose, rosemary, coyote bush, creeping Australian saltbush, ice plant, and the golden bush. So we started with having the water conservation as our main goal, but nowadays another aspect of the project that we are interested in understanding it is the trade-off between water conservation and irrigation-induced cooling, because that's one of the main functions of having irrigated landscape in built environments such as Los Angeles and in general in Southern California. We have this localized urban cool island, or overall we have urban heat island that we can mitigate with the irrigation-induced cooling. But when we push for water conservation, then we limit that because the plants would reduce their transpiration, which is that energy-consuming part. That energy that coming from the sun would translate to increased air temperature. So we are monitoring the temperature of the canopy of these species, and then you can see that we are applying different amount of water, 80% of that reference evapotranspiration, all the way to 20%, which is a really severe water stress. And then we're looking at aesthetic beauty, and then you can see this temperature that is basically going up. You expect to see that from when you start stressing the crops. Here you have, for example, for jasmine, 100° F all the way to 126, which is severe stress, and then bare soil to 40% is even higher than 80%. So we got some good results. This project we have been actually working on it for a number of years. We just finished the second year. So one of the species that was our champion was this creeping Australian saltbush. You see from the aesthetic point of view that even when we reduced the water substantially, so we did 20% evapotranspiration we applied, you see that it's still acceptable, and then the temperature increase was not substantial compared to some of the other species. So that was it. I'm going to stop here. Some of the agencies that supported our research, and I would be happy to answer any question that you might have at the end of this panel, this round of presentation.
Thank you so much.